So for example, let's drop the idea of movie. Think of buying a two-wheeler. When we are buying a two-wheeler, we will not ask to a single friend, right? We will ask multiple friends. We will read the reviews. We will ask internet, and then only we will decide which one we have to choose, right? Right, exactly. It helps us in a better judgment. So the point here is, what I'm trying to make here is, if you have asked your 10 friends and your 7 or 8 friends tell you that this two-wheeler of say Honda is better than TVS, then you might buy a bike of Honda. So, or else if 8 people tells you that no, TVS two-wheelers are better in terms of services, mileage, then you would go with TVS. Simple. So it will help you in taking a better prediction. And how would you do that? By using the majority rule. Majority rule in the sense, you will see how many people are going with prediction A, how many people are going with prediction B. And then you will go with majority rule. Simple, very simple, right? Did you understand this random forest? Now, how does it work? That's important. See, at the back end, it works in a similar way using entropy and information gain. But let's imagine, don't look at the right table. Just look at the left table. You have been given with one data set which has 6 features, for example, and these are your input features. Okay. You're not considering, as of now, we are not considering any output here. I'm just showing you how this, once we have only single data set, how do we come up with multiple trees? That would be a question in your interview. So when we have single data set, what we do, we try to create multiple data sets here using the single data set. How? So for example, this is my first data set. This is my second data set. This is my third data set. So if you notice, and this is my 9th data set. This is my 10th data set. So if you notice, guys, in my first data set, what I've done, I've taken some random samples out of this with only 2 records and with 5 columns, any random selection of 5 columns. I've not taken column 4 here. Now using this data set, we will try to predict the output. So similarly with this data set, I'll try to predict the output with this data set. So these are all random samples which I'm taking out from the main data set. Similarly, in the 9th data set, I'm taking more samples. Okay. So, and the one important thing which you should understand here is bootstrapping. So we know how to do the sampling analysis, right? For example, I have 100 numbers and I'm taking a sample of 10. Now, once I take the sample of 10, say I'm getting the samples as, say, let's assume 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Now, once you have taken the samples out, then when you take a second sample, you should take that second sample again from the same 100 data set, not from the remaining 90. You should take from the same 100. So for example, to give one more example, say you have a bag with 10 balls, okay? Say 5 red balls and 5 black balls. Now, if I want to take a sample of 2 and first, let's say I have taken a first sample, I got 1 red and 1 black. Now, if I want to take a second sample, it should not be a sample from the remaining balls. This sample should be in such a way that you are keeping this first sample back into the bag and then you are extracting second sample. So what I am doing? I am taking the sample with repetition or selection with repetition, and this sampling with repetition is called bootstrapping. See, otherwise we will be having lack of data, right? We cannot come up with multiple samples then. See, for example, if I take this as one sample, then I will left with only very less data, right? So to get with multiple samples, which will help us in our prediction, we should have to get a better prediction, we should ask more friends. Similarly, to get better prediction, we should take multiple samples. To get the multiple samples, we should do sampling with repetition, and that is called as bootstrapping. And then based on the majority rule, you will decide which one to go ahead with. So how to decide? But will it have negative impact as the data set is increased by duplication? See, now imagine in this way. If you have one of your friend ask you the same question and he tells you, yes, you should go and watch this movie based on some questions. Similar to that, if you have another friend who has asked the same ditto questions to you, and then based on the answers which you tell, he will also recommend you the same thing, right? Yes or no? Yes. So this is the first thing. If there is a duplication, I'm telling you, it will not impact the result in decision tree or random forest. It might impact in your linear regression and logistic regression, because there you will working with equations. Here you are working with rules. And then whenever random forest works, in reality you will notice it will take the samples, but it will not try to repeat the same sample. Did you notice out of these 10 samples, did you notice any of the sample is repeated? In general, I have never noticed that these samples are repeated. Okay. So now the next question is, how do we decide how many samples we should take? Yes, how to get majority I will tell you. Okay. That will duplication impact your result. So I would say it has multiple factors, but yes, if you have the exact duplication, it might impact. Okay, it might impact. I'm not sure. This will help you in answering or analyzing in a better way. Okay, let's imagine. Say you are taking 5 samples, 10 samples, 20 samples. Say your accuracy is increasing. As you are increasing the sample, you are getting better judgment, and then slowly your accuracy will decrease. For example, your accuracy is decreasing. So what does it tell? Asking to so many people sometimes leads your confusion, and what you're talking about duplication, that can also be taken care here. When you take more samples, there might be a chance that random forest might take a sample which is repeated. So what we should do is, we should generally draw a curve of accuracy with respect to your number of decision trees which you are taking, or number of samples in your random forest. Okay. So if you see, if you will notice this curve for sure. I'm pretty sure that you will notice this kind of curve. With samples of increasing decision trees, it might increase your accuracy, and then after that it will keep decreasing. So you will stop somewhere here when you have maximum accuracy. So there might be an impact of duplicate sample, but in general, random forest try to avoid that. But if you keep on increasing the number of samples, then it has to take the duplicate sample, right? It has to take, it can't do anything. So in that case, when your data set is say very small like this, and if you go ahead and take 100 samples, then there might be a chance you might encounter a duplicate sample. Now, how to get a majority rule? In general, the random forest in Python coding, it will already take the majority rule. You don't have to worry about that. Okay. But if you want to do it manually, then you should take a majority rule. For example, if you're taking 10 samples, then 6 would be the majority one, 7 would be the majority one. So now this is how you should identify your optimum number of samples or optimum number of decision trees. And based on that, you have to, or algorithm will decide your prediction based on the majority rule. Now, this kind of algorithms, this random forest or these kind of algorithms are called ensemble classifier or ensembling methods. I think there is some spelling issue with my calc. Ensemble. Okay. So if you remember from English meaning also, ensemble means joining or together, unity, right? Something like that. Random forest. This kind of algorithms are called ensemble classifier, or the technique is called ensemble, or these methods are called ensembling methods, right? Because we are taking decision tree multiple times, right? So we are taking a lot of things together. These are called ensemble classifiers. Okay. So in interview, if someone asks you, do you know anything about ensemble classifier, then you can talk about random forest. So there are several other algorithms which are ensemble classifiers, but the scope of this course is with only random forest. Okay, guys. Now we have learned so many classifiers. Okay. Now how to decide the accuracy? I think I've already talked about this, but still I wanted to talk you on this with the help of this small confusion matrix. Let's say you have, I think while drawing I have drawn in this way, right? While drawing, I think I have drawn in this way. Here it is actual, here it is predicted. But it's not a problem. You can take this as P and this as actual. It's just a definition which gonna change. Not definition, it's the ordering of initially true positive was here, now it is here. It's just that the definition will be the same. When you have actual ones and the predicted is also same, then it is called as true positives. When actually it is no or actually it is zero and the prediction is 1, then it is false positives. And when actuals are no and the predictions are also no, then it is true negative. When the actuals are yes and the predictions are no, then it is called as false negative. Now you must be thinking why I'm talking again on this. Okay, so if you remember in the previous sessions I have already told you, you cannot decide your algorithm just based on the accuracy. Different domain problems will have its own different parameters to come up with the better algorithm. Every time accuracy is not a measure. Sometimes there are different parameters which would be a measure. How? Let's see in that direction. Okay. Now let's say true positives. There are where the cases in which you have predicted yes, that means they have the disease and they do have the disease. Right? True negative is also same. We predicted there is no disease, but they are in actual also they don't have any disease. But consider this false positive thing. We have predicted a person is having a disease, but they don't actually have the disease. This is called as type 1 error. In interview, they will ask you what is type 1 error and what is type 2 error. False negative. We have predicted no, but they actually do have the disease. This is called as type 2 error. So with this disease example, say my accuracy is 99%. Say I have two scenarios again. Scenario A, scenario B. In scenario A also I have 99% accuracy. Scenario B also 99% accuracy. But in scenario A, I have false positives, say some 1%. I'm just talking in terms of percentage, but this will be numbers, okay? False negatives are 0. In scenario B, false positive is 0. False negative is 1%. Now tell me which scenario is important. Let's say this is only 98% and say this is, okay, let's go with first 99% to make things simpler. And then I will try to change this problem. Let's compare first apple to apple. So A is better because see, you have to think in terms of as being a patient here. We have predicted a person has a disease, but he do not have a disease, that is false positive. If it has a false positive, then what he will do? He will go and he will do the checkup, right? But in false negative, we have predicted no, but they actually have the disease. That's a type 2 error, right? So we should try to diminish or try to come up with a model which reduces your type 2 error, because that is severe in this case. In your case B, if you notice, false negatives are 1% of the patients are false negatives. That is severe problem because a person is having a disease but we are not able to predict that. So for this clinical trial, Accuracy is not much important. What's important? How much we are able to diminish our false negatives. Let's say my accuracy here is 97% and say false positive are 3% and false negatives are 0. Tell me which is better now, A or B? Which algorithm is better? Don't think in terms of algorithm. You should think in terms of being a patient. Think in terms of being a human being here. Which is better? Which is better algorithm, A or B? In terms of mathematical algorithm, B is better. But in terms of business case, A is better because A do not have any false negatives. So this is how you have to consider, you have to understand which parameter is more important. Similarly, we have several more parameters. I will go with some more parameters, and there are a lot more parameters in outside world which you can always go through, but I am taking some more parameters here. So these are some more parameters here. Accuracy you already know, guys. So when I'm writing total means true positive plus false negative plus true negative. So accuracy you already know. I don't have to tell anything here. Misclassification rate. It's very simple. As the name suggests, it's 1 minus accuracy value. If you have 90% of accuracy, then misclassification rate would be 10%. So what could be the formula? False positives plus false negative divided by total, right? So this is misclassification rate. What is true positive rate? This is important, guys. You should remember. In interview, they will ask you, what is recall or what is sensitivity or what is true positive rate? This is true positive rate, not true positives. This is true positive here. Here it is true positive rate. So what is true positive rate? When it is actually yes, how often does it predict it as yes? So true positives divided by actual yes. That means true positive divided by true positives plus false negative, right? But when it is actually yes, how often does it predict yes? So when it is actually yes is this, and how often does it predict yes? That is true positive. So true positive divided by true positive plus false negative. So for some organizations, accuracy will not be a matter. The measure of performance would be recall for some organizations. They always try to improve the recall. So this is a clinical trial example, is one of the examples for recall, where you will not look for accuracy, you will try to improve your recall value. And how do you improve your recall value? What is recall? True positive divided by true positive plus false negative. To improve your recall, this should be as small as possible, right? So this example is a recalls. In our engineering problem, we generally go with accuracy, okay? That's okay. But I'm just telling you, for different domains, different parameters are important. Did you understand, guys? What is recall? Now let's go with false positive rate. When it is actually no, how often does it predicted? Yes. When it is actually no, how often it is predicted? Yes. So false positive divided by actual no's. So that means, what will this be? False positive divided by true negative plus false positive. Okay. True negative rate. When it is actually no, how often does it predict? No, simple. It is also equivalent to 1 minus of false positive rate. Why? Why is it so? Because your false positive rate is false positive divided by true negative plus false positives, right? This is your false positive rate. What will be a true negative rate? True negative divided by true negatives plus false positive. So when you add these two, you will notice that will be equal to 1. That's the reason true negative rate is also same as 1 minus false positive rate. And this is also called as specificity. Now, precision. Okay, this is precision. What is precision? When it predicts yes, how often your prediction is correct? It is true positive divided by true positives plus false positive. So in my projects, what I do, I always look at precision value. No, it's not similar to TPR, no? What is TPR? TPR is true positives divided by true positives plus false negatives. When it is actually yes, how often does it predict yes? Here in precision, when you have predicted yes, how often your prediction is correct? Those two are two different things, no? So in my projects, whenever I do the fraudulent projects or engineering projects, I generally look at precision values also. And prevalence, I have not seen many of the applications where prevalence is used, but you can also look at prevalence. How often does the yes condition actually occurs in our sample? So it's actual yes by total. But I've not seen this much in the real-time applications. Okay, now what happens, guys? Sometimes people will get confused which parameter should be chosen for our performance, whether it is true positive rate, whether it is accuracy, or whether it is true negative rate or precision. So there are several other performance parameters also, but I'll tell you one of them, which is called as F1 score. So what is this F1 score? This F1 score is a combination of two different parameters here. It's a combination of true positive rate and precision. It's a combination of recall and precision. So people generally, so that they are on a safer side, they have created one more measure for performance, which is a combination of recall and precision. Simple. Okay. Now I have some questions, guys, for you. Let's say that you are doing some prediction, or let's say that you are doing some classification problem of whether a car is Mercedes or BMW, and you have some historical data. In the historical data, let's say you have some images of cars and this is your output. You have some images here. Okay, you have some images. By looking the images, let's say this is being classified as Mercedes, this is classified as Mercedes, this is classified as BMW, and so on. So this is your historical data. Okay, and this has been already classified. Okay, now let's say that this has been classified manually. Okay, this has been, let me go to this here. Yes, this is better. Because historical data what we have is being done it manually by a human being. Okay, it's being done by a human being, and based on that, in the future, then only we can do machine learning, right? Once we do not have historical data, you cannot implement machine learning, because machine learning is all about data. Okay, so let's say you have images. See, in this course, you will be only working with structured data, which is a numerical data. Now I am taking an example of unstructured data, which you will be learning in advanced course. But let's take an example so that it could be easy to understand. Okay. Let's say you have some images of cars. Please forgive me for my images drawing. Okay. Let's say this is Mercedes, this is BMW, this is BMW, this is Mercedes. Now I have millions of data set like this. Now tell me, the human, they can also, so what we are doing manually classifying whether it is a Mercedes or BMW by looking at the images. Similarly, this has been done manually, right? Manually, someone has looked at the image. They have classified whether it is a Mercedes or BMW. Manually, we have looked at the second image. We have classified whether it is a BMW or Mercedes. So tell me, can there be human error here? Yes or no? Yes. So let's take that. There is a normal human being, H1. there is one automobile engineer, say HA, okay, and these two guys have done the classification of these images. Because some images can be blurry, so there is always a chance that there might be some error. So when a normal human being is doing this, let's say there is an error of say 3%. When an automobile engineer doing this, let's say the error is 1%. Okay. Now this is called as the base error. Base error by which we are comparing. So human base error, right? This is called as human base error. Okay. Now out of these two, which one we should consider as a base error? 1% or 3%? So it depends on the, see, in general, we go with 3% as the base error, and then we perform our machine learning algorithm, and we always target that our algorithm should try to achieve an accuracy of greater than or equal to 3%, because most of the machine learning algorithm cannot beat the human error. Nowadays, there are some advanced machine learning which are called as deep learning. They are able to beat the human error. Okay, sometimes, but that is very difficult. Okay, there is lot of calibration which is done at the back end, but in general it is very difficult to beat the human error. And if we are considering this as a human error, human bias error, then it's even further difficult. Okay, so let's say that 3% is my human base error. What is this? Human base error. If human error is known and calculated, won't we correct it? Okay, think in this way. For the historical data, you can always correct it. But how about for the test data? Because on this, see, this is manually what we are doing for human bias error. But in data science, you are not doing anything manually, right? This has been done manually for us. Once we have achieved the manually data set, this would be our training data set, and this should be used. This training data should be used for our machine learning to train our model, and then this model should be implemented on test data set. Now imagine for 10 million data, if the 3% error is there, how much will that could be around 0.3 millions. Will someone go back and correct this? If someone has so much patience, yes, they can correct it. There is no harm. They can correct it. Okay. But if you remember, our objective is that comes later, correcting the error. How is it calculated? Someone has done that. But imagine in this way, someone has done the calculation manually that there is a 3% error and corrected it. Just imagine in this way. When we implement machine learning algorithm on training data set, how will you correct your machine learning model? That's the question. See, manually you can correct it, but how will you calculate? See, when a human is able to come up with this error when he is doing manually, think when machine learning is incorporated on the training data set, will it not be able to come up with the error? Of course it will. Why? First of all, for that we have to understand, because you are asking very advanced question, let me tell you why this 3% error is there. This 3% error is there because there might be an image which is from the side view. If there is an image from the front view or the rear view, you would be having the logo to understand. As a mechanical engineer, we also know the bumper shape, that would be different for Mercedes-Benz and for BMW. But if you have the side view, then someone has to go for that, searching for that car which is there in the image, and then they have to identify whether it is Mercedes or BMW. That's again a different task. What you are doing is you are improving your data set, which is right thing to do, but is it worth it for our machine learning model? That's important. See, again, if it is a clinical trial problem, then you have to go back and correct it. But for engineering problem, it might not be required. we might live up with some 97%.